Hello everyone. Hope everyone is doing fine. Hope everyone is staying at your home. Please stay at your home. Do not go out. Do not get risk getting coronavirus. Now, because of this COVID-19 situations, we are not sure when our college will be reopened again. So we are turning to video lectures. Now, the reason for me doing this video is to let you know three things. One, I'll my approach in doing this video lecture will be I'll be writing on a digital board and I'll be talking over that, stating the concepts and all the equations, which means you will not be seeing my face after 15 to 20 seconds of this video. It will only be the digital board and me talking over the video. Number two, I'll be uploading these videos onto YouTube. It will be easy for me and for you to view also. Number three, see, even though I tried my level best to make sure there are no errors in the video, there are no discrepancies in audio and video, there are certain things that I have no control over. Which means there will be some issues in terms of audio and video for some people, mostly, not everyone, for some people. So I'm extremely sorry for that. Please bear with me. And if you have any doubts, if you are not sure what I've taught, if you have any feedback, any suggestions, please feel free to comment in the YouTube app or comment in the Google Classroom app. I'll make sure I'll reply to every comment of yours and make sure I'll clear all of your doubts. And if your suggestions and feedbacks are valid, if they're very good, I'll make sure I'll implement it from the next video onwards. So enough of me talking right now. Let's dive down into our lectures. Now we'll be starting our unit number 4. The first topic in this unit number 4 will be characteristics of laminar flow. Let's see what it is. Characteristics of laminar flow. What is a laminar flow? That is what we'll be dealing with. Last chapter, while dealing with last chapter, the first thing that I taught you people was an experiment conducted by a scientist named Reynolds, that is Reynolds experiment. In that we dealt with Reynolds number. What is Reynolds number? Reynolds number, the formula is rho Vt by mu or rho Vl by mu, where rho is the density of the fluid, V is velocity of the fluid, d or L is the hydraulic mean depth, and mu is the dynamic viscosity. Now, we have already seen that Reynolds number is the ratio of inertia forces to viscous forces. This is inertia force. We can write Reynolds number as Vd by mu by rho, where Vd is inertia force and mu by rho is viscous force. So now, the two things that are very important when you consider laminar flow is, first thing is fluid particles flow in layers. That consider this is a pipe, and the fluid particles will flow layer by layer. There won't be any intersection between those particles, and the velocity will be low. The velocity will be low for a laminar flow. See, here we have already written rho Vd by mu or rho Vl by mu. Why we were taking d is because flow through pipes. In pipes, the hydraulic mean depth is equals to A by P is equals to D only. That we already derived. I'm not going to derive that right now. So now, I already mentioned this to you in class. I don't know if you remember it or not. When the Reynolds number is less than 2000, the flow is laminar, and if it is greater than 4000, it is turbulent flow. So, in order to determine whether a flow is laminar or turbulent, the main parameter that we use is Reynolds number. So, Reynolds number, what can we say from Reynolds number? In Reynolds number, it is Vd by mu by rho, which means as velocity increases, Reynolds number also increases. So when velocity increases, Reynolds number increases, which means the flow will change from laminar to turbulent. As velocity increases, Reynolds number also increases, which in turn changes the fluid flow from laminar to
turbulent, which means velocity plays a major factor in determining whether the flow is laminar or turbulent. Okay, now this is all fine. These are the important points that we should keep in mind for a laminar flow. Let's go into more flow related theory. See, if there is a pipe, consider there is a pipe, there is flow going inside the pipe, water is flowing. Since we have considered laminar flow, what happens? No fluid layer, that means no fluid layer will intersect. These are all fluid particles. They'll go in straight lines, they won't intersect with each other. They'll go in the same way. If this is the pipe, the black line is the pipe, the internal is the fluid flow. Since there is no intersection between these fluid particles, there won't be any intersection, which means no turbulence, no mixing up of particles around the line. But flow happens. We know by nature flow happens when there is a decrease in the concentration or pressure. Like we already learned when dealing with venturimeter and orifice meter stuff, when flow happens in the direction of decrease in pressure, direction of pressure decrease. This is nature. This is by nature what it happens. So, as there is flow happening, each layer there won't be actually this much gap. Actually, you can write like this. So, when you consider it as flow, from a higher point of view, the layers will be closer to each other, closer. So at some point, one layer will exert some sort of force on the other layer. One layer will exert some force on it. This force is termed as shear stress. Shear stress is a very familiar term for civil engineers. Shear stress is something which makes a particle or a fluid deform in the tangential direction. So if there is fluid flowing like this layer will exert some pressure force on this layer. Simultaneously that layer will exert it on the downward layer, and it goes on like that. This shear stress varies in magnitude from the pipe wall to the internal center of the pipe, which means, let's say, shear stress is termed as tau. So shear stress is tau. Shear stress is tau. Tau at wall, here this is wall, tau at wall will be maximum, which means at the wall the shear stress is maximum. Why it is maximum? There is a solid layer. The wall of the pipe is solid. It will almost exert higher pressure on fluid than a fluid on a fluid. I mean, a solid wall will exert higher pressure on the fluid than a fluid. Okay. Now, what happens to tau at the center? Since it decreases, since there is no actual solid here, there are only fluid particles here. What happens? Tau decreases, there is shear stress decreases, and at the center shear stress becomes 0. Shear stress at center of the pipe is equals to 0. So tau at center is 0. Tau at wall is tau maximum. That is, at wall shear stress is okay. Now what we said, tau is tau maximum. That is, at the wall shear stress is maximum, and at the center shear stress is 0. So the concept of shear stress, why it is important? Because since there is, the flow is flowing in layers, decrease in shear stress, that is the shear stress which is at the wall and in the between the fluid particles and everything, they offer certain resistance. That is, shear stress, the shear stress that we spoke here and here, whatever it is here, they exert certain force on the fluid particles, which is they resist the movement of the fluid particles. So what happens when there is resistance? Something or some property of a fluid should be used in order to overcome that resistance. Like say for example, when you are going on a bike, there will be resistance via friction from the air, friction from the road, and all those stuff. So what will happen? You accelerate, which means fuel. The more energy you produce out of fuel, it will be dealt in dealing with the resistance. Here, in a fluid flow, the resistance offered by shear stress is dealt with decrease in pressure. That is, only force that the only way flow will happen in a pipe is because of decrease in pressure. That is, at point 1 and at point 2 there is shear stress between the layers of fluid particles, which means this shear stress decreases the pressure decreases the pressure uh, between these 2 points, and hence pressure at 2, that is P2, will be less than pressure at 1. This condition is worth only if it is in a horizontal pipe, this like this. Otherwise it won't matter. That will be different, that will be dealing in another. So what you have to remember here is shear stress causes decrease in pressure. This is an important point. What is shear stress? We know in our first unit only we dealt with tau is equals to mu du by dy. This shear stress is here an indication of viscosity. That is, shear stress means viscosity. That is, as viscosity increases, there will be higher reduction in the pressure, which means the more the viscosity, the more the reduction in the pressure value between considerable 2 points. That is what is the meaning of shear stress causes decrease in pressure is.